Welcome to This Explainer. Today, we're diving into an absolute magic trick. We're going to look at exactly how computers manage to render hyper-realistic 3D graphics without literally melting your hardware. You know, if you've ever found yourself totally lost in a massive open-world RPG, or maybe a hyper-realistic racing sim, you've probably marveled at just how lifelike everything looks. Well, you're about to discover the ingenious software sleight of hand that makes all of that possible. And the crazy thing is, it's not just about throwing more processing power at the problem. It's about fundamentally outsmarting the physics of rendering itself.
So how exactly do computers render all this reality without melting down? We all expect stunning realism nowadays, right? Perfect shadows, glowing skin, dynamic reflections. But here's the massive roadblock. Doing the complex math required to simulate that reality 60 times every single second is a virtually impossible problem. The sheer volume of calculations needed to figure out how light interacts with every single object and texture is just staggering. Honestly, if a computer tried to calculate all of that entirely from scratch, frame by frame, the hardware would absolutely buckle. The fans would spin up to max, your frame rate would drop to a total crawl, and that immersive experience completely shattered.
As this quote from our source material perfectly highlights, evaluating pixel shaders consumes a growing share of the computational budget for real-time applications. Basically, as we push for more and more realism, the graphics processing budget is pushed to its absolute breaking point. Pixel shaders, those tiny programs that decide what color every individual pixel should be, are eating up a massive chunk of our processing power. Add complex lighting to the mix, and that budget vanishes in a blink.
Okay, let's ground this by looking at one of the absolute heaviest rendering challenges out there. It's called BSRDF, or Bidirectional Surface Scattering Distribution Function. I know, it's a mouthful, but simply put, while standard rendering assumes light just hits a surface and bounces straight off, BSRDF calculates how light actually enters an object, bounces around inside it, and exits somewhere else. This subsurface scattering is exactly what gives things like tree leaves, a glass of milk, or human skin their soft, lifelike glow. It is absolutely crucial for realism. Without it, characters look like they're carved out of hard plastic. But mathematically, calculating all those internal light bounces in real time is a total nightmare for your hardware.
Just imagine a beautiful, translucent 3D model, maybe a dragon figurine. The light isn't just hitting it, it's penetrating the surface and scattering all the way through. Computing that soft, glowing light from scratch for every single pixel on every single frame is mathematically grueling. To get that stunning effect, the computer is evaluating insanely complex equations nonstop. If developers had to brute force this math to keep the game running at 60 frames per second, the whole system would grind to a halt. Doing it the hard way just isn't an option.
Section 1. The Spatiotemporal Cheat Code.
So what's the clever software cheat code here? How do developers get around this massive mathematical bottleneck? The secret lies in something called spatiotemporal coherence, which is just a fancy, highly technical way of saying that at high frame rates, there's actually very little difference between consecutive frames. Think about it. A fraction of a second later, the camera might shift a tiny bit, or a character might move, but the vast majority of the pixels on your screen haven't changed their fundamental appearance at all. The lighting is the same, the materials are the same, so forcing the computer to recompute the entire screen from zero over and over again, it's a huge waste of energy.
This perfectly illustrates the trick. When we map out what's actually changing on screen during an action sequence, the red areas represent entirely new calculations, like when a character moves and reveals a new background behind them. But the massive green areas? That is pure computational savings. Those green pixels represent surfaces that were already visible just a tiny fraction of a second ago. Why on earth should the system recalculate all that incredibly complex lighting when we can just steal the answers from the past?
Section 2. Reverse reprojection explained.
To pull off this open book test, the system uses a sleight-of-hand mechanism known as reverse reprojection caching. Now, older rendering methods tried something called forward reprojection. They basically took old pixels and tried throwing them forward into the new frame. But because things are constantly moving and rotating, that forward-throwing method caused super ugly visual glitches and gaps. Reverse reprojection, though, works backward. As the computer draws the brand new frame, it looks back in time and natively gathers the exact samples it needs from the previous frame. It completely sidesteps those old visual glitches to guarantee a flawless image.
The crucial point here is this highly efficient logic loop. First, the system calculates exactly where a specific point was located in the previous frame. Second, it checks the depth using a 3D depth map called a Z-buffer just to make sure that part of the surface wasn't hidden behind a wall or something a moment ago. And third, if it's a perfect match, a cache hit, it just reuses the complex math from the past. If it's a miss, only then does it actually do the hard work to recompute.
And what makes this hit or miss logic so incredibly powerful is that it happens entirely within the pixel shader on your GPU. The graphics hardware is handling the heavy lifting natively. That means it completely avoids creating data bottlenecks or sending a ton of traffic back to the computer's CPU. The GPU just quickly checks the cache, decides if it's a hit or a miss, and routes the work instantly. Plus, because of how it's designed, the memory cost is tied to your screen resolution, making it incredibly lightweight no matter how complex the scene gets.
Section 3. Avoiding stale data.
But of course, there's a catch. If we just blindly copy the past forever, our beautiful lighting gets totally stale. Glossy reflections and soft shadows need to physically shift as you move, or the illusion breaks immediately. The cache has to be continually refreshed. Now, one way to do this is the tiled refresh policy, which forces specific blocks of pixels to recompute on alternating frames. But unfortunately, that can leave these sharp, highly visible boundaries on the screen. You end up with a fresh tile sitting right next to an older tile, and it creates this checkerboard artifact that our eyes pick up on right away.
So let's look at an even better solution, the randomized refresh method. Instead of updating chunky, obvious blocks, this method uses a randomized pattern to distribute the updates pixel by pixel across the entire image. It seamlessly trades those sharp tile lines for a high-frequency film grain style noise. And the beauty of this? It's pure biology. Our eyes are highly forgiving of fine, rapidly changing noise, making the refresh cycle virtually undetectable. The lighting stays perfectly up to date, and you never even notice the trick happening behind the scenes.
Section 4. Beautiful, fast results. So what is the ultimate payoff for managing this invisible cache and skipping all that math? Well, when you analyze the visual data, the actual degradation from stealing past pixels is almost totally unnoticeable. By carefully choosing to only cache the lighting elements that don't change drastically when you move your viewing angle, like that subsurface scattering we talked about, the visual illusion of reality remains absolutely pristine.
And the performance payoff? It's huge. By skipping the heavy math, researchers measured an instant 30% frame rate boost when rendering that incredibly demanding translucent shading. 30%? In real-time graphics, and optimization like that is a game changer. It is quite literally the difference between a sluggish, unplayable mess and a buttery smooth, immersive experience. They clawed back a massive amount of performance completely for free just by reusing what the computer already knew. And because of these brilliant caching tricks, developers free up enough budget to achieve a whole suite of cinematic effects in real time. We're talking stereoscopic 3D rendering for VR, rich motion blur, perfect depth of field, and beautifully soft shadows that ground objects naturally in their environments. They can do all of this without skipping a beat, all because they saved so much power on the foundational lighting. Understanding how developers manipulate time to fake reality, literally stealing from the past to render the present, leaves us with one thrilling question. As our graphics hardware continues to scale up, what seemingly impossible graphical illusions will become real-time reality tomorrow? The next time you see perfectly glowing skin or stunning cinematic blur in a digital world, remember the invisible, time-traveling cache making it all possible right before your eyes. Thanks for joining me on this explainer, and keep your eyes open to the magic behind the screen.